This is a slightly different example. This is how we call this function. So we allocate a variable and then pass that, the address of that variable to the function with the in-out parameter. So you can see that this is not quite as messy as it was last time, but we still see some inefficiencies. When we declare the variable, we still see this alloc box instruction. So the variable, the storage for the variable x is being allocated dynamically and with reference counting. That's obviously suboptimal because we only have a tiny little small and nice fluffy local variable that didn't escape anywhere or wasn't captured by a closure. So it doesn't need to go on the heap. Therefore, it should go on the stack because we don't want to pay the price of a heap allocation for every local variable. If we wanted to, we might as well just program in JavaScript. So if you take a look at the canonicalized code, you can see that there is not much that has changed in this code. The alloc box instruction, which is a heap allocation again, has been promoted to an alloc stack instruction, which is obviously a stack allocation, or maybe even just a register when it comes to machine code generation. So this is nice and efficient. And also, you can observe that the integer literal is now just the plain old construction of an int struct, whereby in the previous slide you could see that it was an actual function call to the constructor or the initializer of the type int. Even more memory. The next class of non-pessimizations I'd like to explain to you is, I can say, it's quite well architected because, of course, we are speaking about ARC. ARC stands for automatic reference counting, and you might be familiar with this term. This is an automatic memory management technique that is used by Cocoa and Swift and Objective-C rather than having a tracing garbage collector. And as Cocoa developers, you might well be aware of how much superior ARC can be with regards to performance and reliability compared to tracing garbage collection. But it still has its own limitations, right? So it has kind of slow operations because actually incrementing and decrementing the reference counter of an object, as I mentioned before, these reference counts are stored in a global hash table. So you have to go and acquire a lock because your application might well be multi-threaded. And you have to acquire that lock and then poke around in the hash table and then release that lock. So especially in like a tight loop, you don't want to pay that price, right? Especially when these reference counting operations are redundant. So the compiler has to eliminate redundant reference counting operations. Let's see how this works. In the first example, I have just defined a dummy empty class, foo, just so that I have at my disposal a reference counted class, and then an empty function which just has an argument of that of type foo, and then the real work happens in the juggle foo function. We first instantiate this foo class. We store the reference or the pointer to the generated object into the variable f1. Then we copy that variable, we put it into the variable f2, and then we pass it to useFoo. And of course, the point of automatic memory management is that when you are leaving the scope, all the allocated variables are being destroyed, and for convenient semantic reasons, they are being destroyed in reverse order of construction. So first, a release instruction of f2 is inserted by the compiler, and then a release instruction of f1. And this is indeed exactly what happens. Of course, I have cleaned this code up a little bit because it's a lot messier when it comes out of the compiler, but this is very similar to what actually is generated. So you can see that the instantiation code corresponds to an allocation of a reference counted heap allocated box. Then we are calling the initializer of the foo class, and then we are storing the object back into the storage pointed by the pointer. Then when we assign F2 to F1 to F2, then we are seeing the load of just the row pointer, so that %5 register is now the storage for the F2 variable. And of course, because this is a strong reference, we do a strong retain of that reference. Then we are just passing it to the function, apply is the function call operation in CL, and then, as noted before, we first release the register corresponding to F2, which is %5, and then we are releasing the register corresponding to F1, which is %0. So this is totally expected and same. But what if we modify this code a little bit? You can notice that I have removed the call to use foo. So there is no more function call in this code. What that means is that the strong retain of F2 is immediately followed by the strong release thereof. That means that we've got a redundant retain-release pair. Of course, we would like to get rid of them, and indeed the compiler does exactly that. So you can see that basically the first part, the allocation, instantiation part, hasn't changed at all. But now the copying of the reference is now just the copying of the row pointer, and there is no strong retain. There is no strong retain of %5. And at the end of the scope, there is no release either. It is only the %0 register, which is F1, which is being released. So the compiler has correctly eliminated this redundant release and retain pair. And of course, this is just a very, very naive optimization. This is actually done by the CLGen pass, so this is not even row or canonical CL. Row CL itself is emitted like this. But there are more sophisticated ARC optimizations in the compiler that come handy when you are writing a lot of object-oriented code. Now, let's talk about another fundamental abstraction, functions. On the right-hand side of this image, you might see that it's quite ridiculous where you are trying to unify utensils. So you got monstrosities like norgs and spives and splades. What's even that, right? That's stupid. But if you are unifying functions, that's a good thing. And what I mean by unifying functions is that you can treat all sorts of function-like entities in your language in a uniform way. So some of you guys might have programmed in C++ at some point. You know that in C++ there is a variety of function-like entities, like function objects and lambdas recently, and function pointers and members and member pointers. And these are all incompatible because they are incompatible at the binary level, and the language exposes that to the higher level. But in Swift, we only have functions as such, just functions, no member functions, no methods at the type level, no closures at the type level. If you've got a certain type of function, you can pass anything to, you can use anything in that place. This gives us a sort of semantic clarity and uniformity, and this not only lowers the learning curve for the language, but it also makes it not only easier to learn, but easier to write correct code in, and it also makes your code clearer and nicer and more maintainable. So we should pay attention to function optimizations, function-related optimizations, because we are using functions in Swift all the time, and we are using them all over the place because, as you might know, Swift is a functional language, unlike some other languages which are dysfunctional, but let's not talk about that. I have written a small function called getAnswer, which is very simple. It's really trivial. It just returns a number. But I have also written another function, increment result, which accepts a parameter of function type. You can see that it has the same type as getAnswer. So what I'm trying to demonstrate here is the difference between a direct call to the getAnswer function and an indirect call, i.e. passing that function into increment result. So since getAnswer is just a simple bare function, it's like a function in C. It has no hidden self or context parameters. It doesn't capture any external variables. So we expect a direct call to it to be efficient and simple and the direct call instruction at the hardware level. But we also, at the same time, want increment result to work with all kinds of functions. So we want to be able to pass a closure to increment result, which means that it has to accept a closure. So it has to take a closure as its parameter at the seal level, because functions are annotated as closures or bare functions at the seal level. And so we want this to compile. And indeed, it does compile. This code compiles and runs perfectly well. So how does the compiler do that? First, I just want to show you the annotations that the compiler adds to the types. So increment result, as you can see, takes a parameter of type void or unit to int, but it's annotated using owned, Kelly owned, which is just a fancy way of saying it's a kind of closure. There are multiple kinds of closures in Swift. But getAnswer is of convention thin, which means that it's really just a bare function, a C-like function. And indeed, if you look at the generated seal, the direct call is also of thin convention. So this is just normal direct function call. But what happens when you pass getAnswer to increment result? What the compiler does is simply brilliant. At the point of the call, on the fly, it generates a wrapping closure around the bare function. This closure does nothing, but it forwards the parameters and the return value of the function. And of course, for ABI compatibility, because the point is ABI compatibility, it adds an ignored dummy context pointer parameter, which is of course just unused and not looked at by the function body, but it has to be there. But notice that this means that this wrapping closure is really simple, it's short, it's trivial to inline it. It's trivial for the optimization passes to notice that, that this is doing basically nothing and that the context parameter is ignored. So this can be inlined, which means, incidentally, that this kind of abstraction has zero runtime cost and zero space cost, which is brilliant because now you have ABI compatibility between all different kinds of functions and callable entities, but it doesn't incur any sort of runtime penalty on your code. So we have seen some examples, but at this point you might be asking me, why should I care? These clever guys back in Cupertino happen to know how to implement these optimizations, and we are all happy, but why should I know about this? Well, I'd like to leave you with 3 key messages tonight. The first one is that despite of whatever you might have been taught in college, constant factors matter, and so do compiler optimizations, which help you reduce these constant factors. And of course, this means that you should try to write your code in a way that it's not necessarily optimal or fast or performant per se, but you should write in an idiomatic way so that the compiler can recognize it. It can pattern match on it basically and can optimize it well so that you don't have to worry about getting lower level details absolutely efficient at the high level. This is sort of the point of my second item as well. These compiler canonicalizations improve the architecture not only of the compiler, don't be mistaken. Of course, as you can see, they improve the architecture of the compiler because then the compiler can be written in strictly separated, loosely coupled stages. But it also improves the architecture of your program, of the programs that you are writing, since you can afford to write sort of naive but idiomatic code, and it will still run as fast as it should run. And my third message is perhaps the most important today, because it's not specific to compilers and optimization. It's absolutely general. Optimize the fundamental abstractions in your code. Of course, in the context of a compiler, the fundamental abstractions are memory and function calls and, for example, all sorts of details that you might not care about. But this applies to any code base. If you are trying to optimize some code, you should strive to optimize the key abstractions in it, because those are the abstractions which are all over the place. And by optimizing them, you can gain significant benefits. So, just in case somebody is interested in seeing the code or comparing raw CL and canonicalized CL, or learning about the details of the Swift compiler, I have put all my code on GitHub. So please check it out if you are interested in that. And otherwise, if you have any questions, please feel free to ask. Thank you. Yes?
Are there any kind of rules, I mean, in kind of written form, for example, like solid programming patterns, those help me to help the compiler? I mean, you said there are a lot of things about what we should do, but what this exactly means. Are there some kind of written things about this?
All right, so the question was whether there are some kind of written rules that can be followed by us programmers so that the compiler can optimize the code better. I'm wondering if by a written rule you also mean sort of formal rule or formalized rule? Yes, kind of. To be honest, I don't know anything like that, so I don't know about sort of formal or mathematically precise written rules. But the usual rule of thumb is that write your code as if someone were reviewing it constantly. So if your code is idiomatic enough to pass code review by some peers, then probably it's okay, because compiler optimizers are written so that they recognize the most frequently used patterns, the patterns that are the most idiomatic in the language. So if you are writing idiomatic code, you should be fine.
What if I really strongly follow object-oriented programming and I make like a million classes for every behavior I make a separate class, and will this have the compiler or not? I'm not sure about that.
All right, so the question was if I really strongly follow object-oriented principles, and for every kind of behavior and thing I make a separate class, and I have a million classes at the end of the day, will that have the compiler? I don't think so. So the compiler is caring about the sort of lower level structure of your program, and it really doesn't optimize it doesn't try to understand your program at the very high level, at the highest level, where your actual semantics are. It tries to reason about your program locally, so it has to know some of the semantics of your program. But even global and whole module optimizations, which are looking at an entire function and an entire program at once, even they don't, or basically can't reason about the entire high-level semantics of your program. So if you are making the compiler to do more work or generate code that should do more work, of course your program will do somewhat more work. So compiler optimization is not magic. It works well. Sometimes it doesn't work very well. You have to experiment, basically, but you can't just say that compiler optimizations will do everything for you. Yes?
Are these rules automatically turned on, or do I have to switch a switch in the hex code, for example?
Yes, so the question was whether these optimizations that I was talking about are automatically turned on in the compiler, right? Yes, that's the point. So I had this slide about turning off optimizations, right? So what I was trying to say with this, even if you ask the compiler to not optimize anything at all in your code, it will still perform these non-pessimizations. So if you generate a canonical seal using the onan flag, you will get the improved version of the intermediate representation. So yes, these are all by default, and the only way to turn them off actually is to generate raw seal. But as soon as you go past formed, and you can do anything about that.
Have you tried
Yes.
to seal the inspector that in the NS London or Swift London guided?
Yeah, so there is a visualization program called Seal Inspector, written by a member of the Swift London community. It seems nice. I haven't actually had the time to try it in more detail, but for inspecting code generated by the compiler, it's really worth trying out, I think. So thanks for mentioning that. I hardly recommend anyone interested in lower level details like this to try out. All right, if you have no more questions, then I thank you again and see you later.